absolute value inequalities. I'd like to look at a couple of things before we start here. It's been a while since we've looked at absolute value stuff, so I want to do sort of a quick refresher. So remember, the absolute value of x being, say, like 3. Remember, that means that our definition of absolute value was the distance between x and 0, the distance between whatever is inside and 0. So this statement means that the distance between x and 0 is 3. So let's look at that on a number line. So distance between 0 and x is 3. So that means 1, 2, 3. Here's x. But that also means, right, we have two directions here. 1, 2, 3. This is also x, right? -3 and 3. So this means that x equals 3 and x equals -3. How does this translate for inequalities? Well, if we have absolute value of x is less than k, well, what does that mean on a number line? Absolute value of x, again, means the distance between x and 0. So what this is saying is that the distance between x and 0 is less than k. So 0, we've got k. We also know we're going to extend in this negative direction. K away from 0 is k, also -k. So we want the distance between x and 0 to be less than k. So first of all, what is our distance at k? Well, it's k, right? K's distance from 0 is k. So k is not less than k, so we are open here, and similarly we are open at -k. These are not included. But if I take something that's a little bit less than k, right, that distance, the distance between this number and 0, is less than k. So this is included, as are all of the other numbers in here, right? Everything that's less than k is included. These are all of the x values that satisfy this statement. So the way we write this symbolically, of course, is x's between -k and k. If we wanted to write it separately, we would write it as x is greater than -k, and also, less than k. All right, how would that change if it was less than or equal to? Not by much, right? What would we have to change? We still want to shade everything here, right? But what about when we get to k? Now, the distance of k is allowed, right? We want to include it, right? Something that has a distance equal to k is included. So we've got closed points here now. And all that does is change the signs here to be little equal to's also. So -k is less than or equal to all this. All right, how does all this change if we start talking about greater than? Well, now we want our distance from 0 to be larger than k. Where is the distance larger than k? Well, it's outside, right? All this out here. this is further away from 0 than k. So this is what we're including. Similarly, over here, this is what we're including. How do I write this in this sort of symbolic form? Well, we can't do it in this sort of nice condensed way. We have to write it separately because it's two separate pieces, right? So we have the part where x is less than negative k, and we have the part where x is greater than k. But, however, if we look up here, we've been saying and, right? We have both of these. All of the points in here satisfy both conditions here, right? It satisfies the condition that x is greater than or equal to negative k, and also the condition that x is less than k. Something might be greater than or equal to negative k, right? It might be sort of in this zone, but not less than or equal to k, so we don't want to include that, right? Similarly, something might be less than or equal to k, but not greater than or equal to negative k, so we don't want to include that either. Here, we can't say and for these, right? There's nothing that is both less than negative k and greater than positive k. So we actually, in this case, have to specifically say or, right? So it's actually important that we say and here and or here. How does this change if x is greater than or equal to k? Well, similarly to before, we kind of just add closed points, right? Because now we're including that distance of k in our allowable distances, right? So x is less than or equal to negative k or greater than or equal to k. So I just wanted to give sort of a visual representation of what's going on here before we start this so that everyone kind of can get a grasp on what's going on. Really quickly, before we get into the meat of it, I want to do a review of solving absolute value equations. Solving absolute value equations. So let's say we were given absolute value of 2x plus 9 minus 1 equals 9. Well, remember our steps for solving absolute value equations. If you don't remember, I would recommend pausing, going back to your notes on this stuff and sort of looking at that real quick. Our first step is that we want to isolate the absolute value. So we bring this 1 over. We're equal to 10. Once we've isolated the absolute value, then we can use sort of this property from up here, where we know that the absolute value of x being equal to something means that we can split it, we can take the absolute value away and say whatever's on the inside is equal to that number and also equal to negative that number. So we can split this up here, remove the absolute value, set it just regularly equal to what it's equal to, and also set it equal to the same thing with the sign flipped, right? So negative 10. The one thing we had to look at, though, before we did this was make sure that this was positive. Why did we have to do that? Well, an absolute value is always positive, right? So if this was negative, we would always have a false statement no matter what x value we put in here, because an absolute value is never going to give us a negative. So this has to be positive before we can do this split. And that's why we have to flip the sign to be negative. And then we solve. Easy as that. So we've got 2x equals 1 here. So x ends up being 1/2. And we also have 2x equals negative 19 here. So x ends up being negative 19/2. So both of these are the answer. So the nice thing about this is that absolute value inequalities are going to be very similar. We're going to follow a very similar process. The one difference is going to be with equations. When we split in two, we made the sign of 1 negative. Right here we made the sign of one of these negative. We left one the same and we made the sign of 1 negative. With inequalities, we make the sign of 1 inequality negative, and also flip the inequality. That's the only difference. So let's see what that looks like here. I'll even start with the same problem. So last time we had 2x plus 9 in absolute value minus 1 equals 9. This time let's do is greater than 9. So same thing, we need to isolate the absolute value. We have 10. We split now. We remove the absolute value. Last time we said equals 10. This time we leave it just the same. And then for our second equation, we want to flip the sign of the number, so negative 10, and we also have to flip the inequality sign. So what does this give us? Now we solve these both. We have 2x is greater than 1, so x is greater than 1/2. And we have 2x is less than, we bring the 9 over, we get negative 19, so we have x is less than negative 19/2. Let's look at what this looks like on a number line, so it's easier for us to write this in interval notation. So we've got negative 19/2 and 1/2. Both of these are strict inequalities. They're not equal to as well, so these are going to be open. We want to shade in the part that's greater than 1/2 and the part that is less than negative 19/2. Awesome. So our interval notation goes from negative infinity to negative 19/2, parentheses, 1/2 to infinity. That's my answer. So how is this different from the one we did before? Well, before we had same thing, equals 9. We ended up with x equals 1/2 and x equals negative 19/2, right? Because that's exactly where all of this stuff in here, 2x plus 9, these are the x values that make 2x plus 9 a distance of 10 from 0, right? These are the values that makes 2x plus 9 exactly at 10 and negative 10. These are the values whenever x is greater than 1/2 or less than negative 19/2 that make 2x plus 9 greater than 10 or less than negative 10, right? So the distance of this being larger than 10 from 0. Let's say we've got 2 minus x over 4 minus 2 is less than or equal to 1. I bring this over. I have less than or equal to 3. My absolute value is isolated, so now I can split. I write everything as is without the absolute value. And then my second one is without the absolute value, but I flip the sign of the number, and I also flip the inequality. And then I just solve. So I can subtract 2 over to this side, so I have negative x over 4 is less than or equal to 1. Now, when I'm solving for x here, I want to get rid of the 4, and I also want to get rid of the negative. I can do that by multiplying by negative 4, right? Then I would have x on this side. But when I multiply by a negative, when I multiply or divide by a negative with an inequality, what do I have to do? I have to flip the sign, right? So I've got x is greater than or equal to negative 4. I'll do the same thing over here. Let me subtract this 2 over to this side. I've got negative x over 4 is greater than or equal to negative 5. I again need to multiply by negative 4, which means I have to flip the sign. So I have x is less than or equal to 20. I check out a number line. Negative 4 and 20. I shade in between, right? Because I'm looking for greater than negative 4 and less than 20. My answer is bracket, negative 4, 20, bracket. One more in our notes before we go to the lab manual. So let's say I've got negative 2, absolute value 3x plus 1, absolute value less than or equal to 8. I have to isolate the absolute value. So my first thing I should do is get rid of this coefficient. So I divide by negative 2. When I divide by negative 2, I have to flip the sign. And I have negative 4 over here. Now, before I move forward, remember when we were talking about how we have to check for negative numbers on this side with absolute value equations? We also have to check for negatives for absolute value inequalities. The reason for that is that if we look at this, right, I have absolute value greater than or equal to negative 4. What are absolute values always going to be? They're always going to be positive. Absolute values are always going to be positive, no matter what number I put in here for x. So, if I have a positive number, how often is that going to be greater than or equal to a negative number, any negative number? Always. It's always going to be greater than a negative number, right? So, the answer for this one, if we just look at this, is going to be all real numbers, right? Any number I put in for x is going to give me something that is greater than a negative number. So I would recommend just sort of being on the lookout for negatives when you're doing stuff like this. It'll save you a lot of work and sort of this extra thought process that you have to go through. If we were to continue like this, here's how it would play out. So we would split here. We would have 3x plus 1 is greater than or equal to negative 4. And we'd also have 3x plus 1 is less than or equal to positive 4. We would solve. We have 3x is greater than or equal to negative 5, so x is greater than or equal to negative 5/3. You don't have to write this down, by the way. If you can kind of remind yourself, always check for negatives, and I'll write that here. Always check for negatives. So if you feel confident with this, you don't have to write any of this down, but you're welcome to. So I got x is greater than or equal to negative 5/3, and 3x is less than 3. So x is less than or equal to 1. Well, if I look at this on a number line and I just put these in the way we've kind of been doing, wouldn't I just have the stuff that's between negative 5/3 and 1? Not quite. So we've been sort of loose with how we're using this stuff here. We have to remember that each of these have an and or an or, right? Remember, if we're looking at less than and we split them up, it's an and. Because, for example, if you look at this one, we can be both greater than negative 4 and less than 20, right? That's all of these numbers in here. But remember, with greater than, we have or. So here we've got or. So this is telling us that we either need to be greater than or equal to negative 5/3 or less than or equal to 1. So we can be one or the other. We don't have to be both. So everything that's greater than or equal to negative 5/3 is all this, but also this over here, right? And everything that's less than or equal to 1 is all this, but also this left part over here. So we end up with all real numbers. This is our answer. So check for negatives. Let's move to the lab manual. All right, I'm going to start with number 3. So our first goal is to isolate the absolute value. So of course that probably means we should bring this negative 4 over by dividing. So we've got absolute value of 4 minus x. When we divide by negative 4, what do we have to remember? We have to flip the sign here, right? So less than or equal to, and now we have 3. We split. We have 4 minus x is less than or equal to 3, and 4 minus x is greater than or equal to negative 3, and we solve. So we have negative x, let's bring this 4 over, we have negative 1. We have to divide by negative 1 to get x by itself, which means we have to flip the sign back. So we have x is greater than or equal to 1. We bring the 4 over on this side, we end up with negative 7. We again divide by 1 and flip the sign. So we have x is less than or equal to 7. We draw our number line. We are greater than 1 and less than 7. Because we have this positive number, we can sort of assume that we're just looking at the in-between. And my answer is 1. to 7. Okay, let's look at 4. Okay, so let's bring this 8 over. We have 2c plus 6 is greater than positive 4. So it worked out, right? Even though we had negative to start with, now that we've isolated, we have a positive, so we're good to continue. So we split. We've got 2c plus 6 is greater than 4. We've got 2c plus 6 is less than negative 4. We move that 6 over. We get negative 2. When we divide by 2, we get negative 1. We do the same thing on this side. We have 2c is less than negative 10. So c is less than negative 5. I'm going to draw the number line up here so we have space. We've got negative 5, negative 1. We want to be greater than negative 1 and less than negative 5. So greater than negative 1, we have an open point and we shade above. And less than negative 5, we have an open point and we shade below. So we have a 2-part interval notation, negative infinity to negative 5, union negative 1 to infinity. All right, let's do the next one, number 5. Let's isolate the absolute value. Can I add these together? 4 and 5? I cannot add them together. I cannot add these together. I need to subtract over to the other side first, right? So we've got 5, xy minus 7, negative 4, and I divide by 5. Okay, do we go ahead and split? No, we don't want to split because we have a negative over here, right? Let's think about this. Remember, absolute value is always positive. Is a positive number, any positive number, ever going to be less than a negative number? Is that possible? It's not possible, right? We can't have any positive number being less than a negative number. So this is no solution. So definitely check with yourself to make sure that this no solution makes sense. Check with yourself to make sure that the other scenario where we had greater than with a negative makes sense, that it's all real numbers. Other than that, should be very straightforward problems like this. And that's all I have. Thanks, y'all.